Alright guys, welcome back to Underground Science, and in this video we'll be talking about another example of a weak acid. So we'll be working with the acid dissociation constant, and we'll be talking about another example of how to calculate the pH value from an ice table. Alright, so we'll be working with an ice table again, alright? And we've already done two other examples of this, so make sure to go and check those examples out and those videos out. And so this will probably be our last example, but it's good that we get a little bit of practice of calculating pHs from ice tables so that when we get to titrations, things will be a little easier, alright? So let's go and get started. So we have our problem here. We have a 1.72 molar solution. So remember, molarity is equal to moles over liters, right? We should know that for, so it's equal to moles of solute over the liters of solution, right? So moles over liters. And we should know that for titrations, all right? But we won't be really using this conversion factor for this video. So we have a 1.72 molar solution of aqueous benzoic acid. So another thing to know is that benzoic acid is a weak acid, so we don't expect the Ka to be high. We expect it to be lower than normal because high Ka values indicate that the pH is low and that the acid is strong. Alright, so the stronger the acid, the higher the Ka value, and the lower the pKa value, alright? But the question is, so we have a 1.72 molar solution of aqueous benzoic acid. The question is, what is the pH of this 1.72 molar solution of aqueous benzoic acid? So let's go ahead and start this problem again like we have been doing for the past two videos where we worked with other examples of weak acids. So we already, I already wrote it out just to save time. So we have our benzoic acid here, so HC7H5O2. And because we know it's aqueous, we react it with water, and we know that's going to be in equilibrium because it's a weak acid, right? So that means that it won't fully dissociate into the products, and so some of the benzoic acid will dissociate into the products, but not everything. So let's go and put our ice table down, initial, change, and equilibrium. All right, so what do we say? We said that this was a weak acid, right? And we said in the problem over here, we said we started with a 1.72 molar solution. All right, we started off with a 1.72 molar solution. So we can go ahead and write down that we start off with a 1.72 molar solution. Water doesn't matter because its pH is neutral and its concentration doesn't change. And also, it won't affect our calculation of pH. So we can go and cross that out. We know some of this benzoic acid will dissociate into products, but we don't know how much will. So we say that something will dissociate, some amount, some concentration will dissociate, but we don't know how much, so we indicate it as X. All right? Whatever we lose from this side, we gain in the product side. So we have to put a plus X here and a plus X here, because we're gaining whatever concentration we lost here from benzoic acid. Now, initially, which is what the I stands for, we don't have any products. So initially, we can go and put 0 here. All right, and now all we have to do is just write out the equilibrium part of the ice table. So that's going to be 1.72 minus X. Water doesn't matter. And then, in this problem, it doesn't matter, but water is good for you, all right? And then we add 0 plus X. So that's just going to be X, and 0 plus X here, which is just going to be X here. All right. And now what we do is, because we're working with an acid, right, benzoic acid, we have to have a Ka, or an acid dissociation constant equation, set up. So let's go and set that up. So Ka, we said in our Ka acid dissociation video, was that we do the products, the concentration of the products multiplied together. All right, so the concentration of our benzoate anion, so C7H5O2, and divided by the concentration of the reactants, except for water. So then that's just going to be the benzoic acid right? HC7H5O2. And then we said that, so that's all for now. And next, we look at what can we do to feed values into here. Well, all we have so far are variables, all right? So let's go ahead and see what to put in H3O+. Well, in our ICE table, we see X concentration for H3O+. We also see an X concentration for our benzoate anion, and we see 1.72 minus X as a concentration value for our concentration of benzoic acid. So let's go ahead and feed these values into whatever desired spot that is present in the Ka equation. All right, so let's just go and feed those values in. So next we're going to write Ka, and we're going to go ahead and feed the values in as shown in the ICE table. So the concentration of H3O plus is X, right? So we're just going to put X. All right, sweet. One down, two more to go. The concentration of benzoate anion is X. All right, sweet. So we'll just put X there. And then the concentration of our benzoic acid is 1.72 minus X. So 1.72 minus X. All right. Now we just need a value for Ka, and we can be even a step further into solving for the pH. So what's the Ka value for benzoic acid? You can look that up in a table, and it turns out the Ka for benzoic acid is around 6.4 times 10 to the negative 5. So let's go and put that in. So 6.4 times 10 to the negative 5, all right, is equal to, or actually I did it wrong, it's 6.4 times 10 to the negative, not 6.45, sorry about that. So 6.4 times 10 to the negative 5 equals, and then we just go ahead and, actually, you know what, let's just straight up multiply, right? X times X is X squared, divided by 1.72 minus X. Now we could solve for X using a quadratic equation, because that's what we'll have to end up doing, or we can make our lives easier by assuming that the concentration of X for the denominator is very, very, very low and almost close to zero. If we assume that it's very, very close to zero, we can assume, or we can know that 1.72 1.72 minus a value that's very close to zero will be equal to 1.72, right? It'll be equal to about 1.72. So if we assume that X is very close to zero, or a very, very small number, sorry about that, if we assume that X is a very small number for the denominator, then that means 1.72 minus a very, very small number will also equal around 1.72. So then what we can write is this, 6.4, which is the Ka value for benzoic acid, 6.4 times 10 to the negative 5, is equal to X squared over 1.72. Now we just solve for X. So then we're just going to write 6.40 times 10 to the negative 5 times 1.72, right? 1.72 equals to X squared. If you go and do that, you're going to get X squared equals to about a value of 1.1 times 10 to the negative 4th. All right, so 1.1 times 10 to the negative 4th. Now we go ahead and square root. So we go and do X equals the square root of 1.1 times 10 to the negative 4th. If you go ahead and do that, you're going to get X equals about 0.014. All right, or actually that's 0.0104 is what I meant to say. So 0.0104, or it's just going to be 0.0105 if you round it up. All right, and this is going to be in molarity because we just found the concentration of X, right, of our unknown concentration that dissociated. Okay, well, before I say something like that doesn't make any sense, let's just go ahead and put a question mark here, because now we have to know what good is this value. Well, let's go up to the ICE table. What's the concentration of, actually no, before we talk about that, how do we find the pH of an acid, right? if we know its a hydronium concentration, remember we did a couple of practice problems like that. If we know the hydronium concentration, how do we find the pH? Remember, negative log of H3O plus equals the pH. This is what we have to find, right? This is our goal. So we have to know what the hydronium concentration is. Well, we just found X. What's X? Let's go up. X represents the concentration of hydronium. Well, that's awesome, right? And also benzoate anion, if you want to find the concentration of that also represents X. X also represents the concentration of benzoate anion. And if you want to find out how much of the benzoic acid dissociated into the products, then you can just feed in the X value for here, and you'll find out the concentration of benzoic acid that dissociated into the products. But we need to find the pH according to the problem, right? So all we need is the hydronium concentration. Well, the hydronium concentration here says it's X. Well, what did we just find? We found X. So that means that this value is also going to be our hydronium concentration. What was our equation to find pH? Negative log of hydronium concentration equals pH. So we're pretty much done, right? All we have to do now is just feed it in. So negative log of our hydronium concentration, which is X, right? So it's just going to be 0.0105 equals our pH. So then we write our answer out. pH equals about 1.98. And that's the answer. So if we go back to the problem, what's the pH of our 1.72 molar solution of aqueous benzoic acid? Well, our pH we just found was 1.98. So let's go and write that down. So the answer is 1.98 is our pH value of our 1.72 molar solution of aqueous benzoic acid. All right, and that's it. So I hope this video made sense to you guys. I hope to see you guys in my future videos where I'll talk about more cool topics about biochem, physics, and chem. Don't forget to hit that notification bell, like, and subscribe. See you guys later, and stay safe.